Hello and welcome. Today we are doing chemistry. I will explain to you a chemistry meme, and in the meantime I will tell you why you don't understand pH. So this chemistry meme is actually about pH if I scroll down here. So why is it funny that pH is 17? Why is this soldier suddenly so concerned once he got a pH of 17 on a chemistry test? So I saw this meme on the internet and people were explaining it, and most of the explanations were kind of okay, but no one, or at least most of the people, seemed to not really understand what pH exactly is. So today I decided to educate you all, and so let's jump into it. So what is the joke here? So the joke is about pH, and pH is a scale, so you might have heard about the pH scale. How most people understand it, like people who are not like a chemistry majors would understand pH, is that you have this scale which has the neutral solution, like a pure water in the middle, and then you can make this solution acidic, or you can make it basic, and so you have bases on one of the end of this scale and acids on the other end of the scale, and neutral is 7. Acid is 0, and like a base we go up to 14. So as closer you get to 0, the more acidic the solution, the closer you get to 14, the more basic the solution. And while this is not really a good explanation of what is the pH, if this is your understanding, it's fine. If you are not like working in the field of chemistry, this understanding is not going to get you in trouble. While this is incorrect, it is not like wrong in like a loose meaning of the word wrong. Of course, based on technical definitions, it's very wrong. And so if you just look at this scale, so 17 would be somewhere here, and that is off the scale. So that's why this we use this sad or shell-shocked soldier's image here when he sees pH of 17. So the pH scale might seem kind of arbitrary. Why does it go from 0 to 7 and then from 7 to 14? There are some scales in science which are used, which are kind of totally arbitrary, like the hardness scale, which goes from 1 to 10, and diamond is 10. In the hardness scale, that is not really a measurable physical quantity in like the very strictest sense. It's kind of just comparing different materials with each other. But pH, we have a very strict definition in chemistry, and this is actually something where the number makes sense. So for that, first we have to take a look at what the hell are acids and bases. And so if you put an acid in water, what will happen? So let's think about an acid. So hydrogen chloride, which is looks like this. The Lewis structure looks like this. So chlorine has 7 valence electrons and hydrogen has 1, and well, they make like a single bond here. But if you put this HCl molecule in water, the hydrogen chloride becomes hydrochloric acid, and this is an acid because basically the chlorine wants these electrons more than the hydrogen. So these 2 electrons that are in the bond will move to the chlorine, and we will have this Cl minus ion, and we will have the H plus ion. So hydrogen ion, people will call this a proton because, you know, hydrogen has basically 3 forms. We can have either a single proton, you can have a single proton and a single neutron, that is usually called deuterium, and the symbol for this is D, or you could have a proton and 2 neutrons, which is going to be tritium. That is radioactive. This is why people are freaking out about Fukushima water, because it has tritium in it. So most of the water is actually just like regular hydrogen. So if this hydrogen, of course, so this is the nucleus, so all of them has an electron, generally speaking, but this hydrogen, it lost its electron to the chloride, or the chlorine atom. So we got a chloride ion and a hydrogen ion. So this hydrogen ion is naked. It has no electrons. So the H plus ion has no electrons, which means that when it finds like a water molecule, so water molecule looks like this with the non-bonding electrons. So this H plus ion will easily kind of bond with the non-bonding electrons of the water. It will form this H 3O plus ion, but not all of the hydrogen ions get into this. Sometimes we get another water molecule coming in here, and so both of them will kind of share their electrons with this hydrogen. So we might get something like H5O2 plus, but because this is kind of confusing, mostly we just talk about this hydrogen ion. We'll just pretend that this hydrogen ion is just dissolved in water, and these are just the dissolved forms of the hydrogen ion. And so this was an acid, right? So we define acid as a molecule that can give out this hydrogen ion. It can give this hydrogen ion, well, we are in water, so we add this to the water molecules, and this is how it works in water. So this is an acid, and the base will be defined. There are more universal definitions, but for pH, we can go with this definition of acids and bases. And so for a base, it's going to be the opposite of the acid, which means that if you have a base, then, like, let's say ammonia. So ammonia is a nitrogen with 3 hydrogen atoms, and it has 1 non-bonding electron pair. And if it meets with an H plus ion, then this will just basically bond to the non-bonding electron pairs here. So we will get the ammonium ion, which is the nitrogen with 4 hydrogens and a positive charge. So this ammonia is a base that can become ammonium ion by receiving the hydrogen ion. So whether something is an acid or a base, it depends on whether it can add or receive a hydrogen ion. So this is kind of a more tricky part here, because if you just put water and ammonia together, where does this H plus come from? And well, water can dissociate into a hydrogen ion and this OH minus hydroxide ion. And this is kind of a reaction which goes both ways. So sometimes the water will like fall apart into these 2 ions, and when these 2 ions meet each other in the water, they will join back together and create the H2O water molecule again. So even if you just put ammonia in water, there will be some hydrogen ions in the water, and those can go and meet with the ammonia, and that's why the ammonia will be a base in water. More powerful bases are, for example, sodium hydroxide. So sodium hydroxide is an ionic material. It is actually, when you put it in water, it will just dissociate into sodium ion and hydroxide ion. And of course, the hydroxide ion itself can also receive the hydrogen ion from the water to become water itself. So this is kind of one of the other examples for a base. So now we know what an acid and a base is. And so because everything is just based on the hydrogen ion, so whether we give or receive a hydrogen ion, so defining the character of a water-based solution, how much acidic, how much basic it is, makes sense that we are looking at the concentration of the hydrogen ions in this solution. And for the concentration, we will just put them in this square brackets, and we always, by definition, use mole per liter as the unit of measurement for these kind of concentrations, even though liter is technically not an SI base unit, but who cares? This is a convenient way to describe, so this is what we use. And we use the concentration of these hydrogen ions, but because this can range in a very big range, so for example, if you have, let's say 0.1, let's say you have 0.1 mole of hydrogen chloride and you put it in 1 liter of water, then the hydrogen chloride is something called a strong acid, so it will 100% dissociate into the hydrogen ion and the chloride ion. So that will mean you have a 0.1 mole per liter concentration of your hydrogen ion, but there are some weak acids like acetic acid which will not dissociate 100%. So that means that for the acetic acid, some of the molecules will give up their hydrogen ion and some of them will not. In that case, you can have like very small, like, I don't know, 0.00001 mole per liter concentration. So this would be a very inconvenient way to describe a solution. So what we do when we need to handle multiple orders of magnitude is that we do the base 10 logarithm. And if you don't remember base 10 logarithm from math class, then, for example, log 10 1000 is 3 because 10 to the power of 3 equals 1000, right? So that means that we can describe this based on log 10. So here we have 0.1. For that, the logarithm, the base 10 logarithm is going to be minus 1 because 10 to the power of minus 1 is 0.1. And this is, we have like 5 zeros here in total, I guess. So this is going to be minus 1, minus 2, minus 3, minus 1, minus 5. The logarithm will be minus 5, but we don't want to deal with negative numbers. So we define pH as the minus log 10 of the hydrogen ion concentration. Well, this is what you learn like in general chemistry, maybe analytical chemistry. The actual definition, we will do it in the end, but this is kind of a good workable definition. It's going to work for most concentrations. So this means that if you have some solution like 0.1 mole per liter hydrogen ion concentration, for that the pH will be 1. And if it's like 0.00001, then the pH will be 5. So you can see as the pH goes up, the hydrogen ion concentration is going down here. And that explains why we have the acidic solutions here from 0 to 7, at least as we go up in the numbers here from left to right. So this 0 will be 10 to the power of 0. So this is going to be 1 mole per liter. And then 7 is going to be like 10 to the minus 7 mole per liter for the hydrogen ion concentration. But why is that 7? Why is a neutral solution 7? Well, we already talked about that water can dissociate into hydrogen ions plus hydroxide ions. And if there is nothing in the water, then the concentration of both of these, so H plus will be 10 to the minus 7, and for the OH minus, this also will be 10 to the power of 7, because, well, both of, like, water dissociates into one of this and one of that, so their concentration has to be the same. But, interestingly, for the equilibrium of this reaction will be that always the hydrogen ion concentration multiplied by the OH minus concentration is going to add up, or like multiply into rather, 10 to the minus 14. So 10 to the minus 7 by 10 to the minus 7 is 10 to the minus 14. And what happens is that if you add hydrogen ions into the solution, that it goes up. So, for example, here we have added hydrogen ions to this solution in the concentration of, what was this, 0.1 mole per liter. That means that the OH minus concentration will be a number that we'll have to like multiply into 10 to the minus 14. So that means this is 10 to the minus 1. So OH minus concentration will be 10 to the minus 13. And if we have this 10 to the minus 5 here, then the OH minus concentration also has to multiply to the 10 to the minus 14. So that will be 10 to the minus 9 mole per liters of the OH minus ion, and vice versa. So if you remove the hydrogen ions or add OH minus ions in the solution, then that will mean that, for example, you add ammonia into your solution. That will, the ammonia, so we NH3 plus H plus will make the ammonium ion. This is also an equilibrium reaction, so not all the ammonia will eat the hydrogen ion. But this will reduce the number of hydrogen ions in your water and will increase the concentration of the OH minus ions. And so if you put like the NaOH in your water, that will just directly contribute sodium ion, doesn't matter, but the OH minus ion will be contributed here directly. So if you put like 10 to the minus 3, so that is 0.001 mole per liter sodium hydroxide in your solution, that means that your H plus concentration will be, well, this will be directly the OH because this is 100% dissociating, and you have to multiply to get 10 to the minus 14. So that means that the hydrogen ion concentration will be 10 to the minus 11. So that means a pH of 11. So this is how we got the basic pH above 7, that here the 10 to the minus 14 is the hydrogen ion concentration, and that means that we have in turn 10 to the 0, so 1 mole per liter OH minus concentration. And if you had 10 to the minus 17, so if your pH was 17, that would mean 10 to the minus 17 for the H plus concentration, and that would mean an OH minus concentration of 10 to the 3, if my maths is correct, which is impossible. So water is only, I think, 55 moles per liter. So in water, you cannot get pH 17 without, causing a black hole or something. Well, it's probably not a black hole, but there is not natural density of material that you would need to have over there. Okay, but pH, so pH was the log 10 or minus log 10 of the hydrogen ion. There is nothing in this definition that says you have to be in water. There is nothing in this definition that says that you have to be in water. Any solution where H plus ions can exist can be your medium, and where you can use pH. So, let's say ammonia. So if you can, ammonia is gas under standard conditions, but you can cool ammonia to some, I don't know, minus 50 degrees probably is going to be already liquid in minus 50 in Celsius. But in liquid ammonia will also dissociate into H plus ions, but of course there are no OH minus ions. Here you will get NH2 minus. This is going to be the equilibrium in the ammonia. Of course, this H plus ion will associate with other ammonia molecules, so it will exist as the NH4 plus form, while in water we had this H3O plus and H5O2 plus, this kind of species. Here we will have mostly this proton will exist, or this hydrogen ion will exist as ammonium ion. And so in this case, we also have a similar constant. So here the constant of H plus concentration times NH2 minus concentration, it is going to be 10 to the minus 30. So this is much, much smaller than for water. We had 10 to the minus 14. For water, this is a very, very, very small number. But what does it mean? So in ammonia, the neutral solution, so this is pure liquid ammonia. So I guess I put L here to signify that this is pure liquid ammonia and not an ammonia solution. So liquid ammonia, you will get a pH of what? What will be the pH here? So this also dissociates 1 to 1. So to get 10 to the minus 30, we will have to have 10 to the minus 15 times 10 to the minus 15. So the pH of neutral solution will already be 15. So that is neutral in ammonia. Okay, pH 15 is neutral in ammonia already. So pH 17 in ammonia would mean that you have to reduce the H plus concentration to, 10 to the minus 17. And here the NH2 minus concentration would have to go up to satisfy this to 10 to minus 13. So this is not even like an it's a very mildly basic solution in ammonia, in liquid ammonia. Of course, there are other cases where this multiple can be smaller, and if this multiple is larger, that means like a smaller pH range. If this multiple is smaller, that means a bigger pH range. So in ammonia, you could go from 0 to 30, from acid to base, with 15 in the middle as the neutral. But of course, because nothing says that you can only go to 30, but we don't really talk about pH. So if we go back to water, we don't really go about pH like below 0 and above 14. So in that point of view, while this is for water, this is for ammonia, there is some reason why like this ends of the spectrum. So we already said so that like in water, that 17 pH would mean that we have so many OH minus ions that it would, cause about another black hole, but it would not work with water. And in the other end, so 0 pH just means 1 mole per liter. So maybe you could get like small negative numbers in pH if you had like 3 mole per liter HCl. But this could mean like small negative numbers for pH. And of course you could go the same way, like put like 3 mole per liter sodium hydroxide in your water, and that would be a little over pH of 14. But actually, and now we are going to go into the more complicated things. So until this point, if you have a good general chemistry teacher like me, you would have heard about like these kind of different pH scales in different mediums, but you won't learn about the more deep meaning of pH or the more strict definition of pH in general chemistry. You will have to learn physical chemistry for that, and that is going to be that actually the pH is not defined with hydrogen concentration. pH is defined with the activity of the hydrogen ion. And this works in reasonable ranges because the activity is like almost always the same, like the concentration almost. If the solution concentration, if H plus concentration is low. So what is the activity? And for that, we will have to understand a bit of how solutions work. So in a solution, what do we have? So in a solution, we have some kind of solute and a solvent. And basically, a solution is a kind of mixture in which we have a lot of solvent and only a small amount of solute. So that means that if your solute, let's make this black dot a solute, the solute will only meet with the solvent molecules. So solvent molecules, they mostly like meet each other, and sometimes they will interact with the solute, but the solvent molecules are just so much more of them that this kind of small interaction here with the solute is not affecting the solvent itself much. And the solute itself, on the other hand, is only meeting with the solvent. So the solute, if you have another solute molecule somewhere else, this will be just so much spaced out with the solvent molecules. So solvent is the circle and the solute is the black circle. So these are so far away from each other that interaction between solute and solute basically do not exist. And this has some effect on how these particles, like how these ions or molecules in a solution work, what kind of properties they have. And we can kind of, as we decrease the concentration, that just means we are adding more and more solvent molecules into the same amount of solute molecules. And that just means that we have less and less of them, but because they're kind of their surroundings, it does not change just because I added more solvents between them. That means that we can have a linear relationship. So as the lower amount of solute is in a unit volume of our solvent, this just linearly goes down. So what does it mean? Like, we have some kind of property on the y-axis, and we have the concentration of the solute on this side, and basically it will just go straight up, because as the concentration goes down, this property goes down the same way, and if its concentration goes up, this property will go up the same way. But because the surroundings of the solute does not change, this kind of the relationship stays just like a straight line. But once you increase the concentration beyond a certain limit, there will be changes of the surroundings. So suddenly I have so many the solute molecules in this solution here that interaction between the solute molecules will start to become commonplace. And this interaction will be different. So this, you can either could go like up or down, doesn't matter. And so for the activity, we just cheat and we just take this, some kind of property here, and we'll say that this property with the activity, if I put in the activity here, this will always be linear. So even if my concentration is very high, the activity and the relationship with this property will stay linear. So that means that basically after this point when this linear relationship is not observed anymore, here as the solvent concentration actually goes up, if I take this line from here to go up here, that is a very small change. So in activity point of view, this will be, just a small activity change, even though the concentration change was very big. So based on this activity definition, because you can see that the concentration goes up a lot, but this property does not change that much. So that means the activity will change only a little. So once we get to the point where you would have like a hydrogen ion concentration of around 1 mole per liter, so around the pH of 0, now we are in this part. So now, because pH is actually the minus log 10 activity of the hydrogen ion, well, here, even though I increase my hydrogen ion concentration from 1 to maybe, 5, the activity might only go up from, 0.9 to 0.95. So at this point, even though I can increase the concentration of the hydrogen ion by a lot, I still cannot really increase the activity of the hydrogen ion that much. So the pH will not go down a lot below 0. And because, calculating activity is difficult and, sometimes even impossible, people will use the shorthand for the pH just to use the negative logarithm with the concentration, even in cases when it's not warranted, because that's simpler. But now, you know that at high concentrations, we actually still go with the activity and pretend that, this relationship between these properties and the concentrations, between the property and the activity stays linear. So instead of the concentration where the behavior becomes kind of weird, we just use activity, but then we need to calculate the activity, and we just pushed the difficulty somewhere else, and that is sometimes how science works. Okay, so now you understand the joke with here. We've got here. So even though the chemistry test, like pH 17, does not make sense in water, now you know that pH does not have to be restricted to water. So that is something that if you have a chemistry professor like me, you might get, well, I wouldn't give this kind of problem in an exam. Wait, maybe I did. Maybe I did it one semester, I gave it and no one could solve it, so I stopped giving it as a exam problem. But I definitely give this kind of problems in homework, so the students have a more, like, an understanding. Because, you know, in science, one of the most important things is that you know the limits of the theory, so, like, under what circumstances can you apply certain theories. But I think it is also equally important, or, well, maybe a little less important, but also kind of important, is to not have the limitations which do not exist. So pH is not limited to water, so now you know, and, well, now you know more about pH than most actual chemistry graduates from, like, undergrad. So enjoy your life being smart. Bye bye. Oh, and of course, if you enjoyed this kind of video, leave me a comment and let me know that you want to see more videos like this. This is a new format I just did with my tablet that I've just been laying around for a few years. So I haven't really used it much. And yeah, like the video if you like the video. And subscribe for more random stuff that comes up on this channel. And I will see you next time. Bye.